Log on, tune in, find out. Another good idea from Cambridge.
About some problems better with forecasting, taking very statistical view. Griff is currently at the University of Bath, but he's moving shortly to Heriot Watt to join the EPSRC project, Heriot Watt, Cambridge, Durham. Okay, I'll pass over to Griff.
Thank you. Yeah, so I won't repeat the first slide, thank you. Yeah, so as Stan said, it's a PhD research project and it's at the Centre for Sustainable Power Distribution in Bath. Also part of a consortium called Supergen FlexNet, which is kind of coming to an end now, and a work stream called the future shape and size of the network. So the objective was to develop algorithms that can generate unlimited synthetic time series data sets to represent an hourly averaged wind speed field across Great Britain. And then those time series elements would be time-stamped with time of day and day of year, and they would have distributions that are accurately reflecting the historical data in that way. And the datasets will then be suitable for use in a sequential Monte Carlo simulation of networks, and the resource availability, patterns in space and time and so on, are a very essential part of such simulations, mainly for working out generation adequacy and so on in future scenarios. So of course, as we know, we're entering this period of very radical change in the networks with a considerable uncertainty about the future generation mix. But we certainly know that there's an increasing contribution from renewable generation dominated by wind, and that's going to increase variability and decrease predictability. So there's many challenging questions for mathematicians, and in the short term, there are issues such as calculating the capacity values of additional wind capacity in the current system, or maybe trying to validate in economic terms a decision to increase network capacities or expand the spatial reach of the transmission network. And then in the longer term, and this really was kind of where my work stream was involved in, was kind of looking forward as far as maybe 2050, and kind of looking at the whole range of scenarios that one could have. But these kind of scenarios in general are developed through economic models, which don't make any reference to the spatio-temporal characteristics of supply minus demand. So it's definitely useful to have some kind of way of validating those kind of scenarios. So the calculation of loss of load probability relies on assumptions about the joint distribution of wind resource availability and peak demand. And this is very difficult due to a lack of data. Typically for various locations are only going back a few decades, and since we're only interested in the very peak hours, it kind of leads to quite a small data set. And then in particular in a scenario which includes time shifting of demand and storage, you can certainly no longer make an approximation that demand is independent from its own past values and the past values of generation availability. So that makes this kind of joint distribution a lot more complicated. So calculation of loss of load expectation, of course, through hindcasting using historical real data sets from the past is one way that people get around such things, but the lack of data problem isn't addressed by that technique. So the problem can be overcome by generating synthetic data sets through a time series model, as long as we can have confidence, of course, that the model accurately reproduces the spatial temporal behaviors. So time series models are being used in adequacy studies, but they're mainly univariate, the autoregressive moving average ARMA type. They're mostly trained to reproduce behaviors during peak times only, kind of the winter months and so on, and that is, of course, justifiable when you're kind of relating to analysis of the near future. But some of these, very kind of maybe radically different scenarios, the kind of the peak demand could potentially happen during a broader range of times, and also the loss of load expectation might not be so dominated by the tail of your demand distribution. And so they're generally kind of univariate, sometimes for one location or maybe for the aggregate generation availability. So what I want to try to do is a multivariate model which kind of provides values for regional availabilities. So that will allow full consideration of network effects. So just as an example, I'm kind of showing a cross correlation between a site in the north, in the Shetlands, and another one in Yorkshire. And so these are kind of correlations in time that we have to try to reproduce. The boundaries, in all these plots I'm going to show kind of boundaries, and these are the kind of boundaries of what you might expect from white noise for that size of sample. So anything that's kind of taking place outside of that boundary is considered to be significant. So I'm considering wind only. So the challenge for me was to try to define a single stochastic process which captures the spatiotemporal behaviours of wind on timescales ranging from hour to hour to decades. And my spatial resolution is 20 zones in Great Britain. So I need to try to fully capture very low frequency variability and kind of freak events such as unusually long periods. So for a Monte Carlo simulation, you might typically see 100,000 samples, and in order to do that from a historical data set, you'd need about 490 years. So that very much shows the need for this synthetic sets. And the kind of simpler models are quite stationary, which means that they represent a static wind climate, which of course meteorologists know not to be the case. So my scope was limited to METOF stations from the BADC database, also limited to kind of onshore and close offshore wind farms because of the lack of data available to me offshore. And whereas of course in order to get kind of final wind powers, you have to make some assumptions about the variability within zones and the wind shear and so on. But I'm not focusing on that because I think the same kind of insights would be applied if I had the kind of direct generation data as well. And also to limit the scope, even though the recent work has shown that there might be some kind of trends that we know about due to kind of climate change, they're still quite tentative, and I'll treat them as just kind of temporary or stochastic, and not explicitly include any climate change in the model. So as well as simulation, of course, the models can be used for forecasting, and the fact that there's so much that the computational burden is so much smaller than meteorological models means that it's quite easy to run 1,000 say simulations for a particular period. And then for 1 hour ahead forecasts, you more or less get kind of analytical results for the various percentiles, give or take a bit of number crunching to do with deterministic trends. So the zones are based on 17 zones defined by the national grid, plus an additional 3 zones in Scotland because of the importance of that area. And the zone boundaries intersect the most important interconnectors or weak points in the transition network. And it doesn't really matter the details, but that's kind of giving you an idea of this kind of scale of these zones. So obviously there's a lot of kind of cleaning and sorting of the data that was needed, and I found that I was able to find concurrent 20-year samples, one for each zone, with a pretty good data quality, most of them having about 98% of data present. But because there's obviously 20 zones, that means that 1/3 of ours had at least one piece of data missing, which had to be filled in. And that's again just giving a list of the stations, and hopefully you can see that they're fairly well distributed across the country. This is, of course, is a diagram that's been shown already about this idea of having a viable distribution. Except in this case, as is quite often the case, we see a spike at 0, and this is due to anemometer friction, and it's quite difficult to get rid of it. Also in other locations, we see a spike below the kind of main peak, and that's due to, again, that's just a genuine feature of the actual distribution. So the viable is not perfect, but it's a reasonable approximation. So just to kind of simplify, I first looked at one type of variability was a diurnal trend, and I kind of established that it was pretty reasonable to assume that diurnal trends are deterministic if one can kind of come up with matrices describing what this deterministic trend is for every day of the year, and you can subtract it, and it works fairly well. And this is just showing 2 separate 10-year samples, and they kind of agree with each other quite well. But when it comes to the annual seasonality, here we have annual wind speeds for every month of the year for 2 different years, and we see that even though there's a tendency for the winter to be windier than the summer, in both cases they're pretty different patterns, which makes you think that actually that it's not a very good idea to model annual seasonality as being deterministic. And now this one is showing annual averages at an example 3 zones for the 20-year period. And so we can see that there's kind of, we can see some of these long trends going on, and most sites have a small positive correlation in this kind of series, whereas other ones actually have negative ones. And this is obviously behavior that would have to be reflected realistically in the synthetic data. Now this one is showing an autocorrelation function going up to quite significant lags at 12,000 hours. That's of course about 1.5 years. And what's interesting is that it remains more or less positive for the whole time, even when we're kind of 6 months apart. And this is very much confirming some previous work I've been done, which is suggesting that the wind resource is a long memory process and should be modelled as such. And in fact, rather than just being a kind of simple long memory process, kind of examination of this very distinct peak at the annual frequency kind of shows that it's a process known as a Gargenbauer process. Now, just as a kind of caution, when looking at long memory processes, usually as a kind of validation that it is in fact long memory, this graph here shows you how the variance of an average kind of varies with the size of the averaging period, and when you have the log, sorry, and when you have a straight line, that's an indication that you're dealing with a long memory process, and the slope of that pattern kind of tells you the kind of long memory parameters. But depending on whether you begin in summer or winter, you're getting different values for those parameters. So that was already a kind of slight caution that modelling wouldn't be exactly perfect. Now that's just the kind of defining equation for a Gargenbauer process. So you have matrix polynomials kind of showing how the wind speeds, the past wind values at all the different locations affect the present one. And then on the kind of right-hand side, you have random innovations, and the also you have what's known as fractional differencing, which means that the process is only stationary. You don't need, it doesn't require first order differencing to become stationary. It has to be differenced by a fraction, and that can be understood as an infinite series. So I did fit a long memory model to the data using kind of as initial guesses at moment-based techniques and then ordinary least squares. I did try kind of fitting as well using Whittle-type quasi-log likelihood estimators in the frequency domain, but actually found that the results certainly weren't better, were actually less consistent than with ordinary least squares, and was very expensive computationally. But I'm just doing this one as a sketch. The problem I found was that once I had fit the models, the amount of the theoretical spectrum for such models didn't quite reach the kind of top of that spike, and yet kind of was suggesting that there was too much variability in kind of surrounding regions, and it just didn't. The models just didn't quite fit the spectrum in the way that I hoped that they would do. So I then once tried actually just taking away a deterministic annual seasonality, and found that actually with a kind of the right level of smoothing and doing it the right way, you were able to kind of completely remove that one spike with hardly any effect on all the surrounding spectrum. So that seemed like a pretty good idea. But the process still remains as a long memory one. Smoothing the spectrum in the low frequency range showed that there's still far too much intensity than could be explained by a short memory, or kind of what's maybe is known as red noise more by meteorologists. But with no definite spikes, that of course kind of offers a bit of a problem. So I've just done a sketch here of the types of models I was doing. So I actually found that anywhere that you would choose kind of these kind of poles in this in the kind of model spectrum would be artificial, but by choosing 2 rather than 1, that was a more accurate approximation in general. So I kind of through various kind of smoothing, it was a kind of a process of visually choosing where would be the best place to kind of slightly arbitrarily kind of imagine that the kind of peaks existed in the spectrum. and then again kind of initially kind of visually exploring how various models and their corresponding theoretical spectrum fitted the real one for various values for the long memory parameter. And then to kind of make the search easier, I kind of set one value as being 0.01 and then kind of optimized around that, kind of looking for what kind of combination of differencing parameters led to the best fitting short memory model once that differencing had been done. And so the results were that the spikes in the spectrum were found to take place in periods ranging from a few weeks to a few months. But the long memory parameters, the amount to which the series had to be different to become stationary, was pretty small. And then found that having done that, the best fitting model had the order 3 so third order autoregressive first order moving average. And then also had to do some further. So initially optimized the model as 20 separate univariate models, and then fitted a vector model, a multivariate model, and just kind of tweaked the other parameters around that. Now then, moving on, that kind of took place of kind of the modelling of mean or the modelling of kind of the forecasted values, but then also some kind of nifty bit of modelling was needed to deal with variance, because variance is very much far from being constant. This one's carrying a kind of a scatter plot of monthly variances, so they can vary quite considerably and have some positive correlation with mean. And so I looked at the residuals from my model fitting, which is equivalent to the kind of random innovations that one needs to generate for the synthetic series, and they were quite distinct seasonal patterns, but both in the mean variance and the kind of variance of variances between separate years. So I came up with an algorithm for eliminating that and then reinstating it during the simulating process. But it still left you with kind of shorter term kind of random volatility clustering, and found that kind of periods of volatility or large changes from hour to hour tended to be triggered but by a large negative drop, a negative kind of dip in wind speed. So I certainly needed a model which could reflect that behavior, and the name of that model is an asymmetric power autoregressive conditional heteroskedasticity, which I'm impressed that I managed to spit the words out. But that gives you the equation there describing this process, this way of clustering. And this term where you have the kind of absolute value minus some proportion of its absolute value is where the asymmetry comes in. And actually, so that kind of shows you the probability density of the residuals. So it doesn't really fit a Gaussian. The closest thing was a GED distribution, but that didn't really work for all of them. So I had to do optimization without making any kind of a priori assumptions about the distributions. So that made it quite challenging, but did deliver more accurate results in the end. But I found that when I was doing the simulations, inevitably there would be some kind of period where the kind of variance would end up kind of exploding and becoming extremely high. So actually, that equation for the process couldn't really be used as a means of simulation. I had to come up with a new method in which the value of h, the kind of the scaling factor for variance, doesn't refer to its own past values in the algorithm, and that successfully eliminated the problem and also led to some pretty good results. Maybe that's the time I probably should have left that one out. It's a bit too mathematically dense. But anyway, I had to come up with a kind of way of exploring the joint distribution between the scaling factor and the kind of identically distributed innovations. But actually, as you can see, the results are pretty good. There's actually 2 lines there, one being my simulated results, one being from the data, and they're pretty close. So I was quite pleased that I managed to do that. So another problem is kind of extreme values. Of course, the problem with this kind of model is that the size of the innovation when generating innovations, it takes no notice of how extreme your wind speed is. So even if you're at an extreme value of wind, the simulation process might take you to an even more extreme value in a way that wouldn't happen realistically. So this kind of leads to situations in which the model gives you much more extreme values, and this is something that you have to deal with by kind of capping and redistributing along kind of still extreme but not as extreme values. But as you can see, the results were quite good. This is giving you, the one on the left is a probability distribution for the final wind speeds at a zone. The only thing that it's failed to capture is the kind of lower frequency spike, which you see, but that doesn't have much of an effect. When you turn them into a probability distribution of wind power outputs, you can see that spike doesn't have too much of a problem, and it's a pretty good fit. As another way, I kind of looked at these kind of vector states and tried to come up with a scheme of kind of turning those, splitting them up into kind of 5 categories based on kind of percentiles, and then kind of turn the vector into numbers to make a comparison of how often a certain vector state of wind speed takes place historically and in the synthetic data. And it's not a perfect fit, but it's actually, I think it's kind of quite surprisingly good. However, when you look at the aggregated generation outputs, the historical one is in blue, and the simulated one is in green. And unfortunately, we see this kind of tendency to overrepresent more kind of mixed states, or kind of more kind of moderate kind of levels of generation. So it seems to be kind of underrepresenting kind of global states where the whole of the country is calm, or the whole of the country is going at maximum power. So there's definitely more work needs to be done to kind of represent that a bit more accurately. So I tried to do that. Oh, sorry, before I move on, but this one is slightly better. This one is kind of showing you a distribution of 4-hour ahead changes in the total aggregate generation, and there was a very good agreement between historical and synthetic data sets there. But I tried to deal with this issue of not having underrepresenting global distributions. I tried to come up with a transition matrix model, which is of course very challenging when you have such a high level of dimensionality, and even limiting myself to 4 zones and then 5 kind of wind speed states. But you also need to represent the volatility state because it's because of this clustering. So actually, that you end up with a huge number of states. So even for 4 zones, you have an 8-dimensional vector states, and then that leads to a transition matrix of over 1 billion probabilities. But actually, it did reproduce the marginal distributions surprisingly well. However, after the kind of transforming it back into wind speeds and adding all the deterministic patterns, I found that it actually didn't improve at all on the previous time series model, which, if you look at it together, would be a pajama A patch. Then I won't even attempt to say the whole thing. Yes, so actually, unfortunately, that problem of underrepresenting these kind of global states is something that's not easily cured. Now, looking at autocorrelation functions as well for the synthetic data, for some sites it worked pretty well. This is going up to a lag of 500 hours, and we see that they're in pretty good agreement. Unfortunately, I can't say that every single location had such good agreement. This is one showing much more longer-term lags, kind of starting at 0 and going up to again about a year and a quarter or something like that. And the green is the historical data, and the red is the synthetic. So it's a slightly disappointing match there, I found. And then this one here, for comparison's sake, I then kind of came up with a purely short memory model, which is obviously simpler, and kind of looked at how well that match compared with. So here we have the blue line is the autocorrelation function of the historical data, the green is for the long memory model, and then the red is for just the short memory model. So we see that the green one is definitely better, especially in the range of up to about 200 lags, than the short memory one, which kind of, where the autocorrelation falls far too quickly. But from that kind of 200 onwards, there's hardly any difference, and it's almost actually the case that the short memory model seems to work slightly better from that point onwards, which is, again, slightly disappointing. Also, kind of looking at some means over kind of annual means or means for July and means for January. Unfortunately, well, it seems to be the case that the synthetic model never got them quite right, but it was over the 20 zones, there was an equal number that kind of underestimated and overestimated this kind of variance of means, with the mean average ever in the ratio being about 0.23. And then the variance, what is this? But of course, in the short memory model, as we would expect, in every case it does underestimate this variance of annual and monthly means. However, the long memory model does overestimate the variance of variances for individual months. And in this respect, the short memory model is more accurate, although actually, even though it's more accurate at representing the variance of variances, the actual kind of mean value of variances was still better reproduced by the long memory model. So my conclusion is that I believe that I have correctly identified the right type of process, which is this kind of Gargenbauer process, and also with this asymmetric heteroskedasticity. But there are some disappointing results in there which show that there's still considerable work that would need to be done to really kind of have the level of confidence that it's representing the behaviours on all timescales that we would need to really make any kind of firm kind of deductions about calculating things like capacity values. So yes, it's a slight open question, I think, at the moment about to what extent we can use these kind of techniques as a replacement of hindcasts, and it would be good to have input from other people on that idea. That's the end of my talk.
Again, we've got time for questions. And again, can I start off, because I'm interested in what you're trying to do. It seems that one part of what you're trying to do in terms of philosophy, traditional statistical philosophy is to take limited data plus model and to combine the two to make prediction. Now, in a sense, it seems to me that maybe that's, I just want your opinion whether this is right, but that's maybe what you're doing there, but instead of a closed form analytical model, you're taking existing limited data, your training sets, and you are producing an effect model in terms of a very large synthetic data set, which stands as proxy for a stochastic model. So that would fit it as in traditional statistical philosophy. To what extent could you use that then for real-time prediction, do you think?
Yes, I'm hoping it's going to be fairly good in the kind of 1 or 2 hour ahead kind of patterns. That's the one piece of analysis that I have to do and left over yet. But it is also handy that especially in that one, because it's kind of obviously working on an hourly resolution, this question of my percentiles for the 1 hour ahead prediction at least is given to you almost analytically. You just have to kind of consider what the specific deterministic patterns are for that particular hour of the day and day of the year. But once you've accounted for that, then you instantaneously have this analytical result for the shape of the PDF.
You could use it in real time.
Yes, absolutely. But it's still kind of, I think, about a month's time before I'll have the actual figures for root mean square errors for the prediction on different timescales. But yes, that is very much the beauty of it. And even if, I mean, this model is trained to hourly data, but I'm sure that even on with kind of 10 minutes or minute data, I'm sure the kind of same principles of what model to use would apply. So that would the fact that it can do it so much more simply than meteorological calculations would be even more appropriate if you're making predictions on those much shorter timescales.
It's going to be very interesting to compare with the meteorological approach that gets off the ground.
Just following on from that, do you need, if you think of predicting a year ahead or over periods of time where the long memory parameters would matter, is that all that important? I'm just thinking of things like, say, economic growth or whatever will produce uncertainties in demand over that time period, which may... there are many other things going on over that time period, and I'm just wondering how useful a long-term prediction would be.
Well, it's not really a prediction. It's about kind of exploring what's plausible rather than making a prediction. If you were to generate a synthetic time series without enough interannual variability, it just wouldn't be a realistic data set. So it's not particularly saying that in 10 years this is what the wind is going to be doing. It's just saying that the range of what's possible for the wind to be doing as an annual mean in 10 years' time is this, rather than the range that you would have if you weren't using a long memory model would be far too limited. Well, not far too limited. I thought it would be far too limited. As it turned out, that kind of variance of annual means was only underestimated by about 40 to 50% by the short memory model, whereas the long memory model was in equal amounts overestimating or underestimating, but only by about kind of 10 to 15%.
Andrew?
Yeah, I'm interested in this sort of this long-term memory. If it's not related to annual variation, have you got any sort of physical understanding of why there should be a...
Yeah, well, I mean, I think it is. Ultimately it is, but the model just wasn't quite. Maybe there needs to be some other kind of classification of model, which is somehow able to deal with this kind of. Because clearly, in reality, the annual is genuinely the peak frequency. It's just that this kind of Gargenbaum model was the closest and the one that's been adopted previously just for single locations. But it just there was no set of parameters which could replicate the actual historical spectrum that exists now. So just as a way of kind of fixing that, as you can say, well, let's see what would happen if you took away this annual variability as something deterministic, and it was quite surprising that it was able to do so. So kind of neatly, really, and take away this one single, very, very narrow peak and leave this other kind of much broader area of excess. And then so it's just trying to think of what is the best possible model of doing that, and knowing that those kind of peaks that you decide to give in your model that don't really represent a genuine peak. It's only trying to match as well as you can this kind of general spread of excess variability in the lower frequency area, which just can't be explained by a short memory model or kind of a red noise process.
I've often thought this sort of change in variability, to my mind, it's driven by different sorts of weather patterns moving across the country, and sometimes weather's dominated by one weather system, and sometimes weather's dominated by two different weather systems, or possibly three. And whether, rather than trying to build that into the variability into the time series, one wants something like, I don't know, a sort of hidden Markov model or something to represent shifts in the variability.
Yes, I think you're probably right, but it's a conclusion that I've come to rather too far into my PhD to be able to do that. But that would be certainly something very interesting to look into the future, I think, yes, certainly.
Any further questions? Thank Griff again very much indeed.